Good morning, everyone. I'm Sarat Sreepathi. I'm a computer scientist at Oak Ridge National Laboratory. Today I'm going to talk about PACE, which stands for Performance Analytics for Computational Experiments. So, just a brief history. This started out as a hobby project of mine, and in 2018. So when I looked at some of the E3SM performance data, I kind of felt like, okay, there is a gap we can address by building a solution like this to kind of summarize performance data and deep dive into experiment data, metadata, and performance data as well. So it started out with a couple of summer students. So those are the two, Zachary and Gaurav, helped me set up the initial prototype. And recently, Yongsung Kim joined the team at Oak Ridge, and he's been helping me out with some of the newer features. With that, let's start. So the goals for this work when we started out were basically to kind of collect and summarize the E3SM performance data to interested users and project leads and others, so we can get an executive view of experiment summary performance, as well as deep dive into specific experiments and simulation campaigns and other benchmarks. So the idea is to kind of do a high level summary and then interactively select areas of interest and investigate further. So at the higher level, we track several performance benchmarks, as well as any large simulation campaigns of interest. We are also looking into the idea is to drive some of the performance related research on load balancing and process layouts using data from this. It also helps in identifying computationally expensive kernels, as well as sections of the code for targeted optimization. So to summarize, the overall goal is to first serve as a central hub of performance data and then facilitate all these other aspects as well. So first, I would like to kind of give you an overview of the PACE architecture, so you kind of get the sense of what's behind the scenes. Most of you might actually have seen the PACE web portal, so which is at pace.ornl.gov. So behind the scenes, what happens is on the left, you have various E3SM computational resources. So you have our OLCF, ALCF, NERSC, as well as the dedicated resources that we have like Compy and Anvil. So whenever somebody runs an experiment on these machines, there is a set of data that is collected on that particular platform. So you have your machine files, inputs, experiment inputs, the timing files from that run, as well as some log files. So all the data individually resides in the user's case directory and run directories. So we have several features called the performance archiving, which stores that data in a project-wide location on that machine. So we kind of made the data more accessible through PACE. So what now happens is once the experiment is completed, that data is uploaded into the PACE server. So the PACE server, that's part in the middle. So we have several infrastructure pieces within the Oak Ridge cloud resources here. So the PACE server, we kind of get the data from all the supercomputing machines for the experiments, and then we process and parse that data. So be it model input files, the timing files, some metadata about the experiment setup. So all that information is ingested by the PACE server and finally stored in the database. We also have all the raw data available for further verification or to access other files that are not in the database. So we have three key components there: the application server, which serves as the main kind of central resource for processing and importing the data, as well as interacting with the users. So finally on the right, whenever a user gets to the PACE portal, they interact through the server and then retrieve the data from the database, and then it allows them to do visualizations, performance charts, and other things. So I can get into the features later. So at the overall level, that's the architecture. So these days, any simple website is not a simple website. So behind the scenes, there is a complex system architecture underpinning this. PACE is similar in that sense. So we have I will go through I won't bore you with a lot of it. I will go through briefly some of the technology stack and the choices we had to make when designing something like base. So at the lowest level, you have the infrastructure, the final server that runs most of the stack. So that's on a cloud, Oak Ridge private cloud. So each of these choices in the technology stack, we had to go through extensive evaluation to figure out what's the right fit for our needs. So basically, we have the cloud providers. So basically, we have evaluated private clouds, commercial clouds, as well as the Oak Ridge cloud, and figured out that this is probably the right fit for us. So ORNL cloud gives us access to available resources, as well as we can scale up as needed. We are running a OpenStack virtual machine on top of it, so to provision and dynamically scale resources as needed. The next up from that is a basic web server and a reverse proxy. What that means is you are basically running an application server, and this captures some of the front end stuff and serves some of the static content. So there are other choices also as well, but this is a high performance version, considering something like Apache for these reasons. So then there is a Python Flask middleware. So this is where the heart of the base infrastructure is written. So it's Python along with Flask, which is a web routing kind of framework. So this serves as whenever somebody does a data upload, this intercepts those requests, authorizes those requests, and then processes and imports into the database. So, and finally, there's a file server, which is a high performance object storage kind of stack. So it allows us to store all these raw data files in a very efficient manner and performant retrieval as well. So one of the key aspects is the database. So the database actually is the third generation design variant for this. So basically, initially we have evaluated something like the NoSQL databases called MongoDB and similar choices. So that allows you to have a schema-less approach or a very dynamic schema. So, but for E3SM experiments, we have a lot of structure in there. So I wanted to exploit that structure to make this a lot more performant. So basically, we have figured out MariaDB has the, which is a kind of an open source fork of MySQL. It actually gives us the right balance for there. And finally, we have the JavaScript for the front end. So this slide is a lot of detail, and maybe if anybody has questions, I can delve into it. But I just wanted to give you a feel for what's behind the scenes when you go and utilize this kind of framework. And on the right, we have the visualization pipeline. Basically, whenever somebody requests data on a particular experiment, it starts with some Python web framework code, retrieves data from the database, and then finally JavaScript renders it in a plot of their choice. And finally, last but not the least, cybersecurity compliance at a DOE lab. That's a very big part of getting this done, because if you have ever tried to run any web-based service, or there is a reason why you don't see any sophisticated systems, web-based systems at a DOE lab. The security is a nightmare, and getting it all done and in a compliant manner and in a secure manner is difficult. So we had to get through penetration testing, compliance, and all these other things. So there are so many stories there, but believe me, it's the cybersecurity component is a big headache if you need to get something like this done. So okay, switching gears. So what's the performance data that we collect here? So what's the kind of information that is collected by default? So whenever a E3SM experiment is run, there is always on performance profiling ability within the code. So what we have is basically start and stop timers sections. We use something called the GPTL library. It's a general purpose timing library. So the intention is to capture each application subregion. We kind of look at the time spent within that code. We also aggregate this time across a lot of parallel processes as well. So whenever you're running a program on, let's say, 1,000 MPI ranks, what you're trying to do is gather information from all those and within each application subsection and summarize that. So that ability is there for every E3SM experiment. And what I alluded to before, the performance archiving capability, uh, basically, this is where on every supported platform for E3SM, we kind of gather all the performance data as well as some provenance data for context. So this is usually shared or saved in the project-wide locations on that particular platform. So now with Pace, the idea is to kind of make it more accessible and centralize that information at a single place for easy sharing. So switching gears, so some of you might have already seen and used Pace on a semi-regular basis. So the biggest new capabilities that we have developed in the past few months are basically the ability to do model input parsing. So we have previously had timing data files that are processed and visualized, but we kind of stored the model inputs as a standalone in a zip archive. Now we have gone through and added the capability to process all the model inputs. So basically all your name list files, all your XMLs. So every model configuration input file, besides the netcdf files, we now have the ability to parse that and store it in a search-friendly format, JSON within the database, and then retrieve based on queries. So just to summarize this kind of statistics we have. So we have about 187,000 XML files, 440,000 name list files. There are a bunch of RC files, C maps, RCs, and all the raw data for all these experiments. So if in case we missed anything else that needs to be scanned in the future. So so for now, the total number of experiments is 24. So this was last night around 1 a.m. So now coming to the second big feature that we have added. So previously what happened was whenever somebody completed an experiment on a platform, either they or somebody like the machine point of contact had to upload that data into Pace manually. By that, what happened was, so the kind of cadence to some of the uploads was very split across platforms. So some machines we had regular uploads and some machines we had more sporadic, maybe weekly or a monthly kind of upload cycle. So this kind of had uneven upload statistics into our database. So basically we tried to make this more easier on everyone's part. So nobody so on supported platforms now, we have automated nightly uploads. So this is deployed on Compy and Cori already. So every experiment that is run on Compy and Cori, that data is automatically uploaded into Pace within a day. So it runs at midnight and 1 a.m. on these machines. But so you get so once the experiment is completed, you get the data automatically within the Pace portal by next day. And we are working on Anvil and Theta. So it's just a matter of setting a few more things on those machines. So one thing missing is OLCF, and it doesn't allow automated scripts, testing scripts without two-factor authentication. So once we find a solution for that, that will be there. But most of the platforms that you run your experiments on are already supported, and you will get the data there. So the screenshot on the right shows you, so all those model input files, you can interactively navigate from an experiment. So basically upon selecting an experiment, you can click a particular name list file and then look for, oh, did we set this particular configuration variable for this experiment? So you can easily view and filter. So this feature is pretty new. So I just finished this week. So so this allows us to build upon more capabilities, try to do experiment comparisons, try to see what changed between two particular configurations or comp sets. So there is a lot of things we can play around with once we have all this model metadata. So Finally, I wanted you to take away some of the base statistics right now. So we within the base infrastructure now we have experiments from 151 users. So these are user names. So basically, one user might have different accounts on different machines. So and about 10 platforms. And we track certain performance benchmarks within the performance group. So there's a standardized comp set and resolution and some configuration parameters. We also have data on the simulation campaigns, the Tech V1, high-res water cycle, some of the early science runs we did for the cloud resolving model. We also have the BGC simulation data as well. So if you have other simulation campaigns and you would like those to be added to base, please let us know. You just need some basic details like what's the case names or what's the convention for some of those comp sets and other things. But the data is already there, so it's just a matter of marking those separately and highlighting those. So for now, there are about 24,000 experiments. So one minor detail about that. So when we started out, we were initially, it took us a little bit of time to get to 1,000 experiments, and then by the beginning of this year, we were close to 10,000. I think February was the one when we crossed 10,000, and now with some of these automated uploads and other things, we're getting close to 25,000 already. So I expect this to grow as we do more experiments and everything is captured. So the intention is to capture every single experiment run on any supported platform. So yeah, you get the idea. So we have about 650,000 model input files, 60,000 timing files. So some of the experiments might have more than one timing file based on the MPI ranks of the components and all that. So besides the individual interest into diving into some of the aggregate statistics from these kind of infrastructure can inform, insight and other computer allocation proposals. We can also inform what kind of simulation campaigns we run, what kind of resources we need, so it can even drive some of the computing procurements as well. So I wanted to summarize a couple of graphs that are available through the base portal. So I will get into the interactive section of this. So I will show you some of the portal features, but you can get a detailed tutorial through some of the videos we have posted there. So at a high level, if you select a particular experiment, you can look at a couple of graph types. So a tree graph lets you see what's the amount of time spent in each application or model sub-region. So you start out with a high level overview, and then you can click and interactively deep dive into what you need. Analogous view is called flame graph. So you get everything in a single shot, which also allows, so some people prefer the tree graph approach where you kind of look at fewer information and then select a region of interest. The flame graph lets you play around in a slightly different manner. So these two types are the first charts you should probably go to understand your application performance, and then look into the deeper divers. So some of the so finally, the performance research directions that we want to take. Basically, there are so the process layout and resource allocation problem is a very challenging problem for a coupled model. So what I mean by that is the figure on the left shows a particular run where you see the different components. The x-axis shows you the process number. So this is the MPI rank. So when in a parallel run, you allocate certain resources to certain running certain component, and the y-axis shows you the simulation time spent. So the idea is to lay out these components on these resources in such a way that the overall time to solution is minimized. So if you allocate too many resources to a component which doesn't really have that much work to perform, it's not going to improve your total solution time. So this is a kind of open-ended research problem in itself. So the idea is with these kind of statistics and these kind of benchmarking, we can understand the proper layouts and how if there is room for improvement, how we can actually get to the how we can actually address this resource allocation problem. And on the right, I have a particular chart which shows you the time distribution within the atmospheric component. The idea is to understand what are the hotspots at the higher level, and then also variations across different experiment configurations. So considering something like the low-res model with the high-res model, what kind of computational mix changed, and as we come up with new model developments, how this affects the distribution, relative costs. These are important considerations to understand where to focus our optimization efforts. So I will stop here on the presentation side and switch over to the interactive portion of this. So when some of you might have seen this, so this is the PACE portal. So you can get to this by going to pace.ornl.gov. I will post the link in the presentation as well. So the idea is to look at, so when you first go to the portal, there is a big search box where you can search for any user, machine, or any combination of those. So it does support autocomplete. So basically, if you're looking for a particular experiment with a particular comp set, it gives you the ability to choose using autocomplete as well. So you can do user, machine, comp set, resolution, case name, any of these other combinations as well. So, and then you get the list of the experiments sorted by reverse chronological order. So the most recent ones first, and so once you want to select a particular experiment, you click on it, and then you get the experiment metadata, a lot of the basic set of details about comp set, runtime, model throughput. You get the PE layout diagrams for that particular experiment. So as well as the table, and now you have the ability to see the inputs as well. So when you click on something inputs, now you can look at the particular name list file, and then you can filter down into what you need. So this is one of the newer features. So some of the others that I wanted to show you are basically, so you can navigate by experiments on a particular platforms, or you can go to some of the benchmark results, benchmark simulations, as well as the simulation campaigns. You also have additional resources about search tips and others. So let me show you something like have opened up some of the more interesting experiments to look at. So this is from one of the CMIP6 high resolution run. So you can sort by throughput to look at. No, 1 second. Here. So you can. Looks like a slow internet connection now. So hold on. So as I was mentioning, so some of the other chart types that I wanted to highlight, but basically when you go into this kind of summary tree graph, it shows you the MPI wall max timers across different sections. So at a glance, you can highlight what sections have the most time in your particular experiment run. You can also look at in this tree view where you can interactively dive into things and then look at which timer spent the most time on a particular task. You can also select by threads. There is also this flame graph view. So this kind of shows you the overall simulation time, and then you can dive into, okay, what did Cameron 3, or pick a particular timer, and you can deep dive into it as well. So we have videos on kind of a portal features video, which gives you a more deeper view into some of these features. But I'll stop here and answer any questions.